Paul here with an extremely useful script that will let you solve almost any system of nonlinear equations with which you may someday be faced by using Newton's method. If you haven't already done so, install the numderiv package. In any event, we need to call the library function to make our differentiation functions available, and we might as well, while we're at it, maximize the space on the screen for drawing graphs by putting on some narrow margins. Now let's start with a single variable example of Newton's method. If you've done this in a previous course, I apologize. You might want to fast forward the video, but I find that this is a topic that is not frequently covered particularly well in calculus courses. Let's start with the easiest example, finding the square root of 2 by using Newton's method. You always want to define a function that you can use in an equation of the form f of x equals 0, and in this case the function is not x squared, it's x squared minus 2. If x squared minus 2 is equal to 0, then x is the square root of 2. We want to start with a reasonable approximation to a solution to this equation, and we can do that by drawing a graph of f of x, putting on the graph a horizontal line at x equals 0, and finding a value that makes f close to 0. In this case, in order to illustrate the method, I'm going to choose the value 1.2, even though I could have read a better approximation off the graph. And the first thing you do after choosing your first approximation is to evaluate the function there and evaluate its first derivative there. So we see that the function is negative, but it is increasing at a rate of 2.4. And that's going to give us a pretty good idea of where it might increase all the way to 0. I can illustrate that nicely by adding the tangent line to the plot. So here is a graph in red of the tangent line. That red line is tangent to the curve at 1.2, which means that the slope of the tangent line is equal to the derivative that we calculated at x0, the value 1.2. Now to figure out where the tangent line is 0, where the red line intersects the green line, all we have to do is solve a linear equation, and the solution to that equation is x1, the value of x for which the tangent line approximation is equal to 0, is equal to x0 minus f of x0 over f prime of x0. I've drawn a vertical line at that point of intersection, and that is my new approximation to the square root of 2. If that's not good enough, I just do exactly the same thing again, computing x2 from x1, and now instead of getting a function value of 0.05444 as I got before with my x2, I get a function value of 0.0003. I have shown the place where that tangent line intersects the line that I've drawn in green at a function value of 0, and in this case the intersection matches up so well with the intersection of the green line with the black curve of the function graph that I can't do any better graphically. I can, however, improve the approximation still further, and now my error is only 1.626 times 10 to the minus 8th power, and x3 is a very good approximation to the square root of 2. I suppose we might as well look at it to see what we've got. 1.414214. Actually, it's accurate to more decimal places than that. Now let's try something slightly more challenging. In physics, it frequently turns out to be important to solve the equation tangent of x equals x. My first step is to define a function that I can set equal to 0. That'll be the difference between tan x and x. So I define f to be tan x minus x, and I draw a graph of the function. I'm going to draw the graph from x equals 0 to minus 8, and I'm going to limit the function values that are plotted to lie between minus 10 and plus 10, because on this interval, the tangent function blows up on 3 separate occasions. So there's the function tan x minus x. Let's draw our green line, and you can see that there appears to be one solution to the equation where x is a little bit bigger than 4, and another solution where x is a little bit smaller than 8. In fact, there are infinitely many solutions to this equation, but let's go for just one of them. There's clearly a solution in between 4 and 5, so let's graph the function in between 4 and 5. Show where it's equal to 0, and now it appears that the root that we're looking for is somewhere between 4.4 and 4.6, probably a little bit closer to 4.4 than to 4.5. So let me make as my first guess 4.44. Success in this case is going to be crucially dependent on having made a good initial first guess. We evaluate the function there, we evaluate its derivative there, and we put the tangent line on the plot. And now Newton's method is basically just figure out where the tangent line in red intersects the green line at function value equals 0. And the rule is the new improved approximation x1 is the old approximation to the root x0 minus f of x0 divided by its derivative. So I've indicated that value in the domain by my vertical red line. Now I've got f of x1 equals 0.29. That's not good enough. Tangent of x and x differ by almost 0.3. So I will improve the approximation. And now I'm doing much better. The discrepancy between tan x and x is only 0.017. I've now shown the new approximation with a vertical dashed red line. Let's do one more iteration, and now I've got tan x equal to x to within 7 times 10 to the minus 5th power. I will stop there. You'll notice not only am I converging to a solution to the problem, I'm superconverging, which means that every time I do another iteration, I double the number of zeros after the decimal point. However, if I had made a poor first guess, the result would have been disaster. So let's again graph tan x minus x, say from 0 to 8. We're looking for that function equal to 0. And suppose I said, oh, it's going to be somewhere around 4. We'll try 0.9. Evaluate the function there, evaluate its derivative there, add the tangent line to the plot. Okay. You can immediately see I have done something very dumb. That tangent line doesn't intersect the horizontal green line anywhere near the point where I drew the tangent line. In fact, it intersects it very near to the next root. Anyone can solve that linear equation to get x1, and someone who does this without thinking may not realize that they have done something incredibly stupid. They say, oh, f of x1 is minus 5.9. That's not good enough. I will iterate to improve the approximation, get x2, get x3, and now x3 is a place where we're off by 75. These approximations aren't going to converge to anything. When you're using Newton's method for one variable, if you're careful to draw graphs, you can avoid this sort of silly business, but it's much harder when you are dealing with n equations in n unknowns. So now let's go to two equations in two unknowns. This is a pair of nonlinear equations, log x plus log y equals 3, x squared minus y equals 1. Sometimes, given a pair of equations like this, you can solve exactly for x and y, but most of the time it's impossible to write down formulas that solve the equation, and the only technique you have available is Newton's method. So let's convert these equations into a vector-valued function from R2 to R2, where we can say f of v equals 0. The first component, read in terms of x and y, is log x plus log y minus 3. The second one is x squared minus y minus 1, and we want that function to equal 0. We need a good initial guess, and here I've devised the equations so that such a guess is fairly easy to come by. If I choose a vector whose first component is 3, whose second component is 9, since log 3 is a little bit bigger than log e, like 1.1, the top I'm going to get log 3 plus log 9 is about 3.3. That's not too far off from 3. And 3 squared minus 9, it's not 1, but it's 0. So when I evaluate the function, I discover I'm off by modest amounts in both components. Now I need the derivative. What's the derivative? It's the Jacobian matrix, a 2 by 2 matrix. I compute that. If I were working with a single variable, I would divide by the derivative. What do I do here? I invert the Jacobian matrix and multiply it by it, and the same update formula works. My improved approximation v2 is just v0 minus the inverse of the Jacobian approximation multiplied by the vector f of f0, which specifies how far the function is off. And now I've got an improved approximation to my solutions. X is 2.81, y is 6.89, and when I evaluate the function, I'm not doing too badly. Both components are off by 0.034 and change, but we can do better. Evaluate the Jacobian at this new approximate value, x1. Use the same old update formula to get v2, and now we're really doing great. We are off only by something times 10 to the minus 4th in both components, but we can do better yet. One more iteration. Now we are off by something times 10 to the minus 8th power, and what we've got is an improvement, namely x instead of being 3 is now 2.84, y instead of being 9 is 7.07, and our equations are satisfied with a discrepancy of only something like 10 to the minus 8th. So that's Newton's method in action. And in the two-variable case, again, once the process gets going, it superconverges. So the final example, let's try solving 3 equations in 3 unknowns. The first one is linear, the second one is not, the third one is not. I don't believe there's any way of solving these equations using algebra. There's no formula in terms of square roots and cube roots that solves it. But that doesn't stop Newton's method. First thing we do is we write down a function that we want to set equal to 0. You can see the first component is read in terms of x, y, and z, x plus 2y plus 3z minus 10, and the second two are similar. We make an initial guess, and here, if we're lucky enough to think to plug in x equals 1, y equals 1, z equals 2, we don't do too badly. For example, with the third equation, we've got 2 times 1 cubed, that's 2, plus 1 cubed, that's 1 more to give me 3, plus 2 cubed, which is 8. It's not 14, it's 11, but we're fairly close. So let's hope that's good enough. calculate the Jacobian matrix evaluated at V0. A pain to do by hand, but R evaluates these things instantly. Invert it. If the matrix is not invertible, then we're not going to be able to find a decent solution to these equations. And we use the same old update formula. This will serve you for the rest of your life. Have a good guess to a solution for a set of nonlinear equations. Just use this update formula, and it'll get better and better. Our second approximate solution is x equals 1.0. Y is now up to 1.2. Z is up to 2.2. And I've done very, very well in satisfying the first equation, and half decently satisfying the second and third. But it costs very little to iterate again. And now I'm doing really well. I'm off in the worst case, the third component, still by only 4 times 10 to the minus 2. I'll do one more iteration, and now I have found a solution to this equation where x equals 0.91, y equals 1.26, z equals 2.18, and all three of the equations are satisfied with the discrepancy of only a little bit times 10 to the minus 3, and so I quit. And that is the end of this script.